Dạ, bây giờ mình sẽ bắt đầu cái báo cáo cuối cùng của gặp gỡ mùa hè 2023, lần thứ 14 của gặp gỡ mùa hè năm nay. Tôi xin giới thiệu giáo sư Nguyễn Quang Thắng, hiện là giáo sư ở trường Florida State University ở bang Florida, Mỹ. Thì tôi cũng giới thiệu nhanh đây là Thắng là học đại học ở chương trình cử nhân tài năng khoa toán tin học ở Đại học Khoa học Tự nhiên Thành phố Hồ Chí Minh. Sau đó Thắng làm tiến sĩ ở Đại học Indiana, làm postdoc ở Michigan và Curran. Rồi sau đó là Thắng qua Florida State University làm assistant professor từ năm 2002. Thắng sẽ trình bày về group actions on manifolds, rigidity and local rigidity. Mời Thắng.
Dạ, cảm ơn anh. Đầu tiên là có thể nói xin lỗi trước là có thể slide nó hơi lộn xộn một xíu, bởi vì kế hoạch ban đầu là em sẽ travel Bonn rồi sau đó là nói thoát bằng cách ghi trên iPad, nhưng mà maybe bị hủy nên mới viết slide tối qua thôi. Nhưng em muốn hỏi một cái là em có thể nói theo tiếng Anh được phải không anh Ân?
Yes, please. Just go with whatever you want.
Bởi vì em cũng ít thảo luận toán trong tiếng Việt nên nói trong tiếng Anh nhanh hơn. Okay, so I'm talk about like some recent progress in the Zimmer programs about group action. So maybe let's first start with so what is really the group action? Okay, so what is a group action? So okay, the certainly just like we start with the groups and we have a complete manifold. And by complete manifold, usually I consider Riemannian manifolds, but okay, it doesn't matter that much. So a definition of group actions, when we say the group gamma X on M, then that is just like there exists a homomorphism from gamma into the maps between M. I mean, of course, it must be the image must be bijective map because like the inverse. So, but like, okay, like map between M is usually has like nothing to say about, like so people have to consider like more regularities. I mean, at least for example, measurable maps. But like in the manifold setting, then people like need to consider something, some topology like homeomorphisms between M and M. So that is the mapping bijective and continuous. Or diff K, that means bijective and like has derivative continuously up to order K. Or like sometimes when M has some special structure, then we can consider it like the linear groups or like isometry groups of a manifold. Okay, because I assume that there are, and I also saw there are some undergrad students in here in the audience, so so I want to, I mean, like maybe it's the first time to see the group actions or dynamical systems, and it's really hard to think about. So the really question is how to think about the dynamical systems, because the translations of the dynamical systems into Vietnamese is, I feel it's quite meaningless, and I was so confused about that terms. So for that, maybe I try to give some examples. So maybe the very first examples I give is okay, let me show you the video of the dynamical systems. Okay, so this is an example of a dynamical systems. So okay, so what does that mean? So I mean that is the examples of like just Dow mixings. So like we mix up flowers and things. So we just imagine that like we got a machine that mixes dows together. So like the dows are just like a space, and then, so we do the operation that move in the particles around. I mean continuously, so defensively. I mean, okay, that is one operator, but let's say suppose we got like two machines, and so like we got two operators, so we can do one first and then the second later, and then the second and then first, and so on. So but like not necessary like when the orders of the machine when we use like okay, like whatever the mixing should depends on the orders of the machine that we use. So that means, yeah, like it really now needing, but like the operator is recorded by the group. So that means like we got a group acting on the space of the flower, and as a like mixing it up. Okay. Other examples that it happen more in physics or like in analysis, they like just a flows. So fluid flows. So we got like in the space, we got the some fluid, and then by the times the particle moving around. Okay. And I mean, I just try to give those examples, just give an idea of dynamical systems, but like other examples that I care more about, like the one coming from geometry thing. So let's say suppose we look at the manifolds, and so the manifold has a symmetry, like some symmetry to think of isometry things, and so like we think of like symmetries, like we can reflect the manifolds or like moving the thing around. So that is also like the think of them as a symmetric group acting on the manifolds. Okay, now let's look at linear algebra examples. So that is a linear representations. So if we look at the matrix group, the linear group, so it acts on the Euclidean space by linear transformations. So this is like a standard examples of like a linear actions. And this kind of action has been studied much long ago, but like under the name linear representations. And like especially like at the earliest, one of the biggest achievements in the early 20th century is like many like people was able to classify like linear representations of many groups. Okay, but like just instead of, I mean, okay, now if we think about in manifold, then we can think like not just like action by linear transformations on entire Euclidean space, but it also acts on some nicer space. For example, the sphere, or like the space I write here is just like called the projective space of n-1 dimension. So what is the projective space? So that is just a space of light that we look from the origin. So let's say suppose we just standing at the origin in Rn, and then the direction we look at, like each direction we look at is a point in the projective space. A linear maps will map like a line through origin to a line through origin, so it acts on the real projective space, and R here just stands for the real projective space. And so yeah, that indicates if you replace a real by other field, that is still even finite field. And I mean, more generally, not just a line, but now we can consider the subspace, like two-dimensional subspace, three-dimensional subspace, and or even the more general that I call the flaps. I mean, the collections of subspace that one contains the others. So yeah, like here I just wrote the Grassmannian of K subspace in I. So that is just a space of K-dimensional vector subspace. Okay. I mean, those are the actions very nice, like bilinear structures and very smooth. I mean, because linear, you can differentiate anything, any orders. Another harder to describe, but it's also like very important examples in the settings of action by isometries. That is the examples of linear groups act on the space of inner product on Rn. Okay, it's harder to describe this space, but we can think of inner product on Rn either like the choice of symmetric ellipses in Rn, right? But and furthermore, we can also define like how like the distance between the different ellipses, like just say like how much we have to deform, like compressing or expand in certain direction from one to the other. And that turns out what that matrix, first of all, the space of inner products turn out nice manifolds, and with the matrix, appropriate matrix we define, that manifold has a large symmetries group. So okay, so those are like the core examples, which maybe like the third one and the fourth one is the one that we would like to think about them most in this one, in this case. Okay, so what's the goal? Now we got the goals in study about group actions. Like maybe I should say that because the interaction between groups and manifolds. So usually like especially starting from like mid 20th centuries, or like even before that from Klein, but like people start to look the interaction between the groups and the manifold, because like the interaction does say something about manifolds and also say something about the groups now, and it's a non-several in studying them. So the goal is certainly we want to classify all group actions. Okay, so but this seems to be too ambitious or like too much to ask for, because all groups and all manifold. Okay, maybe not much to say, especially if your group is free. That means like there are no relation between elements, then looks like there are no restriction to do anything. So it's really it's better to ask about like to classify actions of certain class of big groups. So I use the big groups here because like this terminology was used in like Zimmer's or like by Labourie's and like other people, just come from idea. In fact, so like Zimmer's in the results, and then in ICM address, like he proposed a program to classify actions of semi-simple Lie groups and their lattices. So the big groups here, like the class of semi-simple Lie groups and their lattices. Or maybe I should say it's lattice. So how to think of lattice? Just think of like Zn at the subgroup of Rn, right? So it is a discrete, but when you quotient out, you got something like compact one, some nicely. Okay, and in the programs, Zimmer also conjectures that. Okay, so like philosophically, then that means just a big group doesn't act on small manifold. That's the point. So that means like if the manifold has a dimensions is small, or like relatively compared to the acting groups, then the action should be just a trivial. Okay, or maybe I say trivial is just too much, but like should be virtually trivial, because any groups you can take some finite quotient, especially it's like a linear group, then you can just quotient out by some like congruent thing. So like you do modular groups, and you can always get some finite group, and finite group maybe can be realized as just some like finite subgroup of the symmetry groups. So yeah. So like we just say virtually trivial, that means just action is just factor through finite. Okay, like this formulation of Zimmer conjecture is the cleanest formulations. He makes several conjectures in there, but like other conjectures are more technical, require some geometric understanding to stay. So I just say the simplest one, which is the easiest one to understand for exposition. Oh, by the way, if you have questions, just stop me. Okay. So, I mean, the question is why such a program is not too crazy. It's like why we should expect it possible to do any such a classification. So in fact, like Margulis in the 70s, he showed that, okay, so if the actions of linear groups are like in general like semi-simple groups by linear maps, like by linear maps on the Euclidean space, then in fact all such action can be classified using the previous work in the linear representation. Okay, that is great. Right. And in fact, this is I mean, this in fact was like one of the main motivations for Zimmer to propose his programs. Maybe I want to say a bit about this one. I mean, the results would say it has a name, Margulis superrigidity. I mean, like the formulation is like the actions on the actions by linear maps, by linear transformations on Euclidean space, but there are also alternative formulations like a linear action on the projective space, like I said, like because linear maps. Oh, this one should be d-1, not n-1. So that I wanted. So we can think of it like also like the linear actions on projective space also classified. Or there are also another alternative formulations in terms of isometries of like inner space of inner products on R2Ds. Okay. Okay. And in fact, I mean, I want to mention just a few results, the actual rigidity results to point out such a rigidity indeed happen. So, like, remember I said about the conjectures, Zimmer conjectures, and indeed, like, okay, not completely proved, but like in many cases, especially like the cases that easy to formulate, like linear groups, not like general, like special linear groups. Then Brown, Fisher, Hurtado, like in a sequence of papers. I mean, just for this group, then it's only the 2 papers. But yeah, like they verify the Zimmer conjecture, showing that okay, if your groups on your group is a lattice, or like you can take entire group, entire special linear group SL and R, then it doesn't act on the manifolds if the dimension of the manifold is smaller than n-1. So you see there's a thresholds here like n-1 because like this group does act on n-1 dimension, n-1 manifold. I mean, because the example we consider it acts on the projective n-1 space. And that's exactly the threshold. So below that, there are no such an action. Maybe some another flavors. I mean, like another flavors, like when high dimension things, but like more special case. And this also like, I mean, in some sense, this also related to the conjecture by Smells about the existence, like which manifold that supports the anisotropy diffusion. So like Brown, Rodriguez has and one, and also shows like actions of lattice in like SLNR. Oh, yeah, okay. SLNR when n at least 3. Yeah, yeah, like such an actions on torides. Then they also can classify. But I mean, okay, the novelties of the work here is just like they obtain their results in the homeo settings. Homeo settings, but of course there's one condition that is anisotropy action. So anisotropy action just means there exists an elements of the group except anisotropy diffusion. So diffusion. So, and what is anisotropy diffusion? That is the action that has like it's completely decomposed. Like at every place it decomposed. When we look at the derivative, it's going to decompose in a direct sum of 2 directions. One direction is like uniformly expanding, and one direction is uniform contracting. Okay. Yeah, but like when the dimension, like when in higher dimension, then usually like people have to impose some anisotropy condition, or like in general hyperbolic conditions to expect such a rigidity can happen. Okay, so that is rigidity. Like just try to classify all of them. Now about the local rigidity, right? So what does local rigidity mean? So for this one, I have to say something that I hide you from when I talk about rigidity. So first of all, I have to tell what are the topologies on the groups, right? So now let's just consider the action by homeos or diffusions. I mean linear, then it's easy because linear we have a natural topologies on the linear groups already. So like on homeo or diffusion, diff k m. So this is just like the space of function from m to m. And in the space of function from m to m, then there's a natural topology that is compact open topology. That means just like the conversion is uniformly on compact set to define the conversion. Okay, so this is the topologies of the groups. And now what is the topologies of the actions? But remember, an action is just a homomorphism from the group into those groups. So again, it is also like kind of the space of function from one space to another space. So we still can use a compact open topology. So like, yeah, like the natural topologies in the actions are like the groups, homeo diffusions are just compact open topology. I mean, explicitly, I want to tell you explicitly to think about, and that is just like sufficient in most of the situations. So if we consider the group, discrete group that generated by just finitely many elements, then like 2 actions, when we say they are closed, with like each generators represent like homeo or diffusions that are closed in those groups. Okay. And close in those groups are like, okay, if homeo, then we just use the subnorms, and if k, then we use the subnorms of like all derivative thing. Okay, and so now the topologies, and now we have the topologies in the space of action. So now we can talk about like two actions being close by. And so what does that mean when we say that we consider the local rigidity questions? Or like another way for local rigidity is the stabilities, which is maybe more familiar with dynamical systems in analysis or like other fields. So local rigidity just says like you consider certain actions and which is there a way to perturb the action to obtain a new action? Right? And of course, the answer is obviously yes, we can always perturb them by the obvious way, that is like what we call the conjugate. That means we pre-compose and post-compose the action by just some map close to identity, right? So like that means like when we say how hard it is to perturb, that means just how hard it is to perturb actions like up to conjugations. And when we say the local rigidity holds, like if like okay, that means like that action is very hard to perturb in the sense that all the nearby action must be conjugate or semi-conjugate to the original action. Okay, and I mean the last slide, and the slide is just like the definitions of the local rigidity. It just means like we can, the new action is here is like semi-conjugate to the original action, and that whole like for every element of the groups. I mean, if you think Z just like gamma is just Z, then it's just enough to hold right the one single one that represented by one. Okay. So far so good. Okay, so now like okay, like is there any examples of local rigidity? In fact, yes. I mean, the results here come like almost a century now. So like Gilbert's, Calabi, and then eventually the way, I mean, Gilbert and Calabi get some special case or certain class, and I mean, finally we're all settled out by way, like in the mid previous centuries, say, okay, local rigidity, in fact, holds and happen, and but like okay, now I have to tell you which space you have to perturb the action, and like the space to perturb the action is like we perturb the action but still in the linear way, like it acts as a linear maps. So so like if we take a lattice in the special linear groups, and now I mean any nearby linear representations, like nearby like any nearby actions by linear transformations in Rn must be conjugate to the original one. And in fact, this is actually like that's usually people in the rigidity theory mark this one as just like the starting of the starting stories of the rigidity, because this was like the motivations for like later on like Mostaus in like 68, I think, prove his Mostau rigidity. That is like in the sense like you see the local rigidities, and now Mostau rigidity, so there are no local. That means Mostau rigidity is in the sense like global, but not global, but yet, but like there's some extra assumptions, but then I mean the actual really global one is like Margolid superrigidity. But like Margolid superrigidity was also motivated by Mostau rigidity, and then come to the Zimmer program. So. Okay, so I mean, those are classical one. There's some others, but maybe too much to mention. So like, I just want to say a bit about like how to evaluate the local rigidity statements. Right? So remember, in the local rigidity statement, like we have to perturb certain thing. And then we ask if it's like the new one is conjugate to the one. So I mean, of course, like the statement will get stronger if like we allow the perturbation space to get bigger. So that means like we allow the perturbation has less regularity. So action has with less regularity. But still the new action must be still like conjugate to the old one by some math, which has really high regularity. So yeah, like this is the way to improve or like exist local rigidity statement. And of course, like if we do the negation of the statement, then if we want to show something non-rigid, then we want to say even like we perturb the actions in a really small space, but yeah, like there are just no conjugations even with a very low regularity between the old one and the new one. Okay. And in fact, like in this sense, like there are many things open, especially like want to improve the regularity of the semi-conjugation. I mean, most of the questions asking about improving about regularity of the conjugation are mostly open. So maybe I just mention the simplest one where I can stay without introduce many notations, even though it's already a bit complicated to explain. But like, yeah, like in the three manifolds, even three manifold, three hyperbolic manifold of constant curvature, like step one. So if we look at fundamental groups, so fundamental group is just a group of loops in a manifold where we can multiply loop together, because like if we follow one loop and then follow another loop, then we just get a new loop. So there's a natural actions of the fundamental groups of three manifolds on the sphere, which is really just like the covers, the space called the universal covers of the three hyperbolic manifolds, where it's like just technically three-dimensional space. And so there's a boundary at infinity called the S2, like with a homeomorphic to sphere. So like there was a conjecture says, okay, if we perturb in the C2 one, but the conjugate should be C infinity. Even though this space, like this one question is very low dimensions and very explicit thing, but it like more or less fully opened. And not much known. I mean, not just not much known, but not no much idea at all. So yeah, like in the previous work, we verified some very special, very special. So it's not not much at the progress in this lecture, but like with some extra assumptions. Some.
Hi Thang, can I ask a question?
Sure.
So let's say in the conjecture that you start with a smooth perturbation and then C2 close to the original action, and suppose that you can show that it's C10 conjugate to the standard one. So can you bootstrap from C10 to C infinity? That's my question.
Yeah, okay, that's a really good question. And actually that is more like a precise statement of the conjecture. So the precise statement of the conjecture also says, I mean, yeah, like like if, I mean, like of course, like we can just formulate in this sense, but there are also the formulations doing like if we can show if there exists a C2 conjugate, whether we can bootstrap it to like C infinity conjugate. So yeah, your question is also like really the another way to formulate the conjecture.
Okay. Thanks.
Okay, so now I mean I should mention something about what is a new thing because like all the thing I mentioned is very old, like mostly done in the previous century already. So now what is a new thing happening? So like the C0 local rigidity, right? So I just recall the examples. The example I gave, like what's it, like very standard one. So just a linear groups acting on Rn. So by linear transformation, so it also acts on the projective space. Okay. Okay. And now if we perturb this action, okay, then with Chris Connell, Mitu Islams, and Ralph Sebastian, we show that, okay, if we perturb this action, we don't get any new action. Okay, so people always complain about rigidity results and boring results, like because you show they're nothing new. So yeah, so this one says if we perturb actions, and what is the actual statement? That is the action. First of all, it's action by homeo, okay, and the perturb action must be like C0 close to this one. Then the new action is just like semi-conjugate to the old action. Yeah, like this is the like most special case, but like of course the full statement will be like just instead of SL and R, we get some semi-simple Lie groups, and like instead of RPN -1, we got some quotient by some parabolic one. But anyway, like just thinking about this example is already new. Okay, so I just want to emphasize about like what is the really thing news in this results. It's just like we allow the perturbation in the homeo one, and the homeo groups is really a really big groups because I mean because like if we think about this infinity of a manifold, I mean that is infinite dimension, but it's still like kind of like Lie groups, infinite dimensional Lie groups. Diff K, okay, not quite a Lie group, but Frechet space, and so but homeo is even worse. And like the like we perturb and also like just like allowed to be just in the C0 topology, which is more or less like the regularities, yeah, like optimal thing. I mean, but we cannot say anything about the semi-conjugate, the regularity of the semi-conjugates, because under this settings like action by homeos and that I see C0 close, then there are no hope to improve the regularities of this one because of some like danger ties construction. Okay, so I mean, I certainly skipped many results due to the time constraints, but I want to mention a few of them, like mostly like close, like closely related to the one I mentioned. So with higher regularity, there was a work of Chus, Sullivan's, Kanai, Katoff. I mean, Chus and Sullivan's like in like SL2R. Things. Kanai is in SLNR. Cutoff special is in more general one. And like Kapovich, Kim Lee, they make it 2 digits. So so that is like almost C1 like Lipschitz. If you think about Lipschitz, it's defensible almost everywhere. And Kapuscinski just like almost C1. And I mean, there are also some announcements. Some announcement from Regularity has one, and they announced it several years ago already, but the paper still had not come out. So, okay, so like in the setting, like I said, like about Newton, about like C0 thing. There's some work by Jonathan Bodens and Katie Mann, Katie's and Jason Manning, and yeah, but like those in the settings of hyperbolic manifold hyperbolic groups, and like in SLN, like SLNR, I forgot if I mentioned SLNR, but like in the really new things is like n at least 3, which is like not hyperbolic because it has some zero curvatures in there happening. Okay, so I guess I still have some few minutes to talk about ideas, like what's the new thing come in. Yeah. So first of all, the ideas. So maybe I start with some ideas from the old works, like so. The very first ideas is just coming from the hyperbolic dynamics. So there's something called structural stability. I mean, the most generalizations, like general form was stated by Hirschfeld-Schultz, but like it's built on a sequence of many previous work as well, and especially some initial work was in the PDEs. So the structural stability is saying, say, the hyperbolic behavior should be stable under the perturbation. So what is hyperbolic behaviors? So that is the thing that I mentioned before, like where we got the system where we look at the derivative, it's splitting into contracting and expanding. Right. So the basic example is if you look at a matrix that has like all like diagonalizables, but like I mean I make a diagonalizable to make it easy to think about diagonalizables, but like all eigenvalues has modulus different from 1. Right. So that means there will be some eigenvalues have modulus bigger than 1 that corresponding to the expanding direction, and some eigenvalues has modulus smaller than 1 that corresponding with contracting direction. And now if you just perturb the coefficient of that matrix, you still get a matrix of the same behavior. So like that behavior is like stable under perturbation. And I mean, okay, like in the system, like I just give examples of just single matrix, but like there's a set to define the set where the hyperbolic behavior happen as well. And the set is actually also stable under perturbation. So yeah, like I just say, like just think about like matrix with diagonalizable matrix with all eigenvalues has modulus different from 1. There's examples of the cat map on the torus, and like in the topological settings, then it was like by Smell, he defined the horseshoes, where you got a rectangle, you bend it and make it in the horseshoes and intersect with the original rectangle. Right. Okay. And more examples from geometry would naturally arise, would they like consider geodesic flows, which is like the flows on the manifolds, like unit tangent of the manifold, where we look at the unit tangent vectors, and then we look at the geodesic span by that initial vectors and flow it over the time. And in the case of SLNR, when n is bigger than 2, then there are similar objects called wire chamber flows, but like of a higher dimension analog of chamber flows. So there's one problem, like if we just try to use a hyperbolic dynamics. So action on the closed manifolds, especially on the boundaries, are not hyperbolic. So like, yeah, action on a manifold, like a single element may act like contracting, expanding, like has some not so dynamics twinge, but like it's not like everything, and there are always some parabolic thing could happen as well. So Sullivan came up with a way, like even though the actions on the boundaries is not hyperbolic, but there's a way to create the hyperbolic cities. That is creating a new systems. And the way he created called a suspend, like a new system called the suspension of the old systems. So just think like we got a diffeomorphisms on the interval, then we consider it's like by the time, there's a time parameter where we, after the time 1, then we come back to the space, but we start from the surface, and now we walk out of the surface for the like just in a one at the extra dimensions, but by the time 1 we come back, then we come back by the diffeomorphism action. So that is a suspension thing. I mean, one good thing about like a suspension, like in some such situation, after suspension, you got some hyperplexity, but of course you pay back by an extra dimension things. But now, yeah, like with the hyperplexities of the suspension, then the structural stability can be applied. And then, okay, like because you pay some price, and so now you have to figure out the way to how to get back to the original thing. So if you are able to find some relation between hyperbolic set of the new system and the original one, then maybe you are able to say something about that action. And so this is like the way, like when I mentioned about local rigidities of Sullivan, then this is the way the program the idea he proposed. Okay, but yeah, like the problem to follow this idea is just about the regularities, because like hyperbolic dynamics, when the definition is certainly C1, yeah, all of them just work in the C1. So under the C0 settings, it's just like the tool is not available. So what news? Okay, so what news? So the thing new, like to overcome all the issue there, we just like replace a hyperbolic system by some kind of some like transverse folation. So one thing I should mention about hyperbolic system, they were like under the expanding or contracting direction, but not just direction, they integrate into some kind of folations that transverse to each other, called the stable and unstable one, like expanding and contracting thing. And they all way transverse. So now instead of looking at the system, we actually like consider just a transverse folations and replace it with that one. There are some issues. Okay, now structural stabilities we also do not have. But like in this setting, then there are actually some previous work in the coarse geometry actually does have to overcome. Yeah, like structural stability is a statement very infinitesimals. Why it's on the coarse geometry is just an argument of the large scale. So it's a really opposite, but somehow it's not like can replace. So I mean, okay, I just say I still lie a bit, because like actually there, when I say transverse folation, but actually there are no folation at all in the C0 setting. So we have to overcome it by actually there are no folation, but maybe we can construct like some lift individually, even though the lifts can interact each other in a bad way. But yeah, like we build those lifts by like using the ideas by the developing map. Well, first of come up in the like Esmond connections, but were used in wave proof of local rigidities, and later on like Thurston's when he like reinterpret wave local rigidity at the GX structures, geometric structure. And when we develop in, so we have to start from local and then build to global, and in the local one, then we use some barycenter construction from differential geometry. Okay. Okay, I think my time is probably is up. So maybe I just mentioned like all the results I mentioned so far, I just rigid. So I just want to end with a non-rigid statement. So there are some examples of non-rigid one where like the dimension like on a nice manifold, but like the dimension is just somewhat larger one than all the examples other one. Then actually such it become very flexible. So okay, so and I mean, yeah, like in the this is the previously known about like why it's not local, not rigid, and in fact this becomes just a very big field now. So timeless space. Okay, I think that's all.
Thank you. Thanks for the great talk. So are there questions or comments for Thang? Mọi người có ai có câu hỏi hay có muốn bàn luận gì với Thang không ạ?
I have a quick question. So in your new approach, you use the transverse foliation to replace the hyperbolic system. So somehow you are looking more in the image of the action than you look at what the action names, right?
Yeah. Yeah. So in fact, like yeah, like when we do the suspensions, so we should get like a system, a new system, but like actually there are no new system in there. So yeah, like there are no actions or like a system, there are no flows or anything. So we have to do it like just very topologically or geometrically, yeah, and replace it.
Thank you.
Có câu hỏi gì nữa cho Thắng không ạ? Thắng cho anh hỏi câu đơn giản đó là cái C0 rigidity á, là cái norm trong C0 đó là optimal chưa hay là
cái ví dụ này đó là optimal rồi, bởi vì nếu mà rigidity thì cũng là optimal trong cái nó mà action trên cái projective space đó là optimal. Và cái non rigidity này, statement này cũng là optimal, bởi vì thấp là trong cái là topology là C infinity, nhưng mà like no C0 conjugation, nên là nó cũng là optimal.
Thì trong cái một loạt cái replacement mấy cái chứng minh ở Thắng á, thì cái bước nào là khó nhất khi mà dùng cái C0 topology? Tại vì anh không có làm trong hướng này nên không có hiểu lắm, tại vì dùng giữa các cái CK và C infinity ở đây nó rất là khác biệt, cho nên là trong các cái bước replacement này cái bước nào là khó nhất khi mà
cái bước mà là giống như mình phải set up được cái transverse foliation này là cái bước khó nhất, là nó technical nhá. cái bước mà dùng cost geometry thay cho structural stability ấy, thì chắc một phần là do trước đây em cũng có nghiên cứu về cost geometry nên em thấy nó là rất là tự nhiên. Nhưng mà cái bước set up được cái transverse folation, thật ra là chỉ có một transverse folation và cái leapwise là cái khó nhất. Nói chung là cần khá là nhiều cái kết quả từ cái barycenter methods. Bởi vì tụi em muốn set up được mấy cái manifold này á, theo nghĩa là nó không có được cái global regularity, nhưng mà nó vẫn có một cái regularity trong một số hướng, và nó chỉ có continuous trong một cái số hướng còn lại thôi. Thì cái thiết lập được cái regularity trong một cái số hướng đó thì là cái khá là technical, khá là...
Cảm ơn Thắng, rất là thú vị. Có ai có câu hỏi chính thức gì nữa không ạ, trước khi chúng ta chuyển qua phần thảo luận khác? Cảm ơn Thắng một lần nữa. Chắc là chúng ta dừng ghi hình để